16 c sub k, that whole thing is going to have to be equal to 0. Now, another thing to look out for is this is supposed to be true for all relevant values of k. When we say relevant values of k, I mean head back here and say that this is only true if k is greater than or equal to 2. Only true if k is greater than or equal to 2. And by that we do mean a positive integer that is greater than or equal to 2. We're not talking about like 2.5 or e or pi or e to the pi power. That would be ridiculous. So before we get ridiculous, let's go ahead and expand this to the next page and do more math with it. I'm going to recopy this real quick here. K times k minus 1 times c sub k plus 3 times k plus 2 times k plus 1 c sub k plus 2 minus 7k c sub k plus 16 c sub k is equal to 0. Okie dokie. And this is only true if k is greater than or equal to 2. Now, in order for this to be true for all k is greater than or equal to 2, it would make a lot more sense for us to actually solve for the highest index that we see here. So that's what I'm going to do. I'm going to say solve for the c term with the largest index. Again, we will be creating what we call a recurrence relation. A recurrence relation is how you make the c's with the larger indices in terms of the older indices. So, what I'm going to do is I'm going to take everything with a c sub k attached to it, I'm going to move it over to the right hand side. So we'll get 3 times k plus 2 times k plus 1 times c sub k plus 2. That part is staying. Everything else is moving. So that's going to be minus k times k minus 1 c sub k plus 7k c sub k plus 16 c sub k. Now notice that when we do this, everything on the right hand side has a c sub k in common. I would like to factor the right hand side. So I'm going to factor out that c sub k like it's the greatest common factor. Then I'll probably do a little bit more algebra because, I mean, that's just what I do. Alright, let's distribute the minus k through. So we got a minus k squared plus k plus 7k. Oh, I probably should have subtracted that over, shouldn't I have? Yep, that's going to make this problem a lot nicer. Yep, problems tend to be a lot nicer when you do them correctly. So put it all together, we got ourselves negative k squared plus 8k minus 16. To the keen observer, you'll notice that we can factor out a negative from that. We'll have k squared minus 8k plus 16. That is a perfect square trinomial. That is going to be ridiculously convenient for us. So over on the left-hand side, this, I probably should have copied this at every step, but what the heck, it's still there. So to finish solving for c sub k plus 2, we divide both sides by that big nasty thing, and we get the following statement. 3 k plus 2, k plus 1, c sub k. As a quick reminder to ourselves, this is only true if k is greater than or equal to 2. Now, if it's only true if k is greater than or equal to 2, then I have a fantastic idea. Let's start with k equals 2 and start plugging things in so that we can start establishing what some of our later terms are in terms of our earlier terms. Now, we are supposed to come up with 2 linearly independent power series. Oh, look, it's the start of the problem. Find 2 linearly independent power series. 2 linearly independent power series means that we should have 2 free variables. Well, heading back to the last page for a sec, we already know what those 2 free variables are going to be. We were able to get c sub 2 in terms of c sub 0, indicating that if c sub 0 is a free variable, we can now solve for c sub 2. C sub 3 was in terms of C sub 1, which means that C sub 1 is going to be a free variable as well. So here's what I'm going to do. This might be a little bit complicated because I'm going to be borrowing from lots of different sheets now. We're actually going to change the orientation back like this because I prefer to live dangerously. Our two free variables were C sub 0 and C sub 1. To establish values for C sub 2, we were able to do that when we plugged in k equals 0. That was this relationship right here. So I'm going to grab that relationship and use it. Negative 8/3 C sub 0. So this was the case of k equals 0. Then, in the case of k equals 1, we were able to establish another relationship, which was all the way back over here. C sub 3 is equal to negative 1/2 C sub 1. Finally, we now have our other recurrence relation that holds true for all of the values k equals 2. This is where it's going to start to get a little bit messier, but we're going to do it anyway. In fact, I'm going to recopy this relationship over here. C sub k plus 2 is equal to, let's see, reading this off the page, negative k minus 4 quantity squared over 3 times, more reading, k plus 2 times k plus 1, all times c sub k. Alright, this is where we are going to start looking for and trying to establish patterns. I'm going to take k equals 2, I'm going to plug it into this relationship over here, try to neglect as little as possible, be very detail-oriented here. Of course, now that I said that, I'm probably going to screw something up. So, plugging in k equals 2, we'll get c sub 2 plus 2, that's c sub 4, is equal to negative. Up top, that's 2 minus 4, that's negative 2, quantity squared is 4, all over 3 times 2 plus 2 is 4, times 2 plus 1 is 3 times c sub 2. But we've already established a relationship for c sub 2, and that was equal to this guy back here. So we'll get negative 4 over 3 times 4 times 3 times what c sub 2 is equal to. Negative 8/3 c sub 0. Now at this point, you'll probably want to reduce this fraction down a little bit. I really don't need to say 4 over 4 or negative times negative. So let's call this 8/9 c sub 0. Now if you were to leave it in this form, it would probably be a little bit easier to start establishing some relationships, but what the heck. Let's just go for a little while and see what happens. For the case of k equals 3, we're going to head back up to our recurrence relation. We plug in k equals 3. We get a relation for c sub 5. So for c sub 5, this is going to be equal to negative. We'll have 3 minus 4, that's negative 1, quantity squared, so we'll get a 1 up top. We'll still have 3. This is k equals 3. 3 plus 2 is 5. And 3 plus 1 is 4 times c sub 3. But what was c sub 3 equal to? Let's see. 1 over 3 times 5 times 4 times c sub 3 was equal to negative 1/2 c sub 1, which puts it in terms of one of our free variables. Also of note, 5 times 4 times 3 times 2, we could throw in a times 1 for good measure, we would get ourselves 5 factorial. But for now, we'll just go ahead and say, it's 120. But we'll also throw out the fact that it's 5 factorial. OM goodness. Those are two very different exclamation marks for the record. That one's a factorial, and that one's the exclamation mark. Sometimes you just have to exclaim stuff. Now, let's keep going. For k equals 4, this will be c sub 6 is equal to, alright, let's, oh my gosh. Oh my gosh, that's awesome. Why is that awesome? Because that gives me a 0 up top. Which means that the denominator is officially I don't care, and it's going to be multiplied by c sub 4, but I don't care because it's all going to be equal to 0, and I'd put an exclamation mark after that, but then it'd be 0 factorial, and that would be wrong. Now, this also tells us some other stuff. You'll notice that in the recurrence relation, the new term is dictated by the second previous term, which means that every time the index goes up by 2, it'll be a multiple of this. So this is also going to be equal to C sub 8, and C sub 10, and C sub 12, and C sub 14, and so forth and so on. In fact, every even index after C sub 4 is going to wind up being equal to 0. That is so metal. Unfortunately, that doesn't finish up the problem. It means that we need to take care of the odd indices still. So C sub 7, well, that's for the case of k equals 5, so let's do k equals 5. That'll be negative 1 squared up top, 3 times 7 times 6 in the denominator times C sub 5. We'll check this out though. We have a 5 factorial from here, and then we have a 6 and a 7 after that. So that'll be negative 1 over 3 times 7 times 6 times, all right, that seems relevant now, 5 factorial times C1. So we could really call this negative 1 over 3 times 7 factorial times C sub 1. You're going to find very frequently in these power solution problems that factorials tend to pop up. Now, a great question that my students like to ask, how far do we need to take this out? Well, technically speaking, if you're finding a power series, you're finding an infinite number of terms. Do I want you to find all infinity terms? Well, yeah, but unfortunately we don't have infinity time. So, one thing that you can do is try to generalize it. Another thing that you can do is just after a certain finite number of terms, you can stop. So, let's see. For one of the linearly independent solutions, this stops as soon as we hit C sub 6. So we'll have 1, 2, 3 terms in that solution. And then in the other solution, we'll have an infinite number of terms, and it'll take a very, very long time to get through all of those. But whatever, that's fine. All right, now is a fantastic moment for us to say, all right, wait, what were we finding? So let's go ahead and do that. We were operating under the assumption that our power series solution took on the form y is equal to sum from n equals 0 to infinity of c sub n x to the n. So our solution is going to look like c0 plus c1 times x plus c2 times x squared plus c3 times x cubed plus c4 times x to the fourth, and so forth and so on all the way out to infinity. But we have some additional information that we're going to make use of. This is the last page that I had up here. So c sub 0, that's just going to be c sub 0. C sub 1 times x, that's just going to be c sub 1 times x, plus, oh, just kidding, that's going to be minus 8/3 c sub 0 times x squared, minus 1/2 times c sub 1 x cubed, plus c sub 4 was equal to 8/9 c sub 0 x to the fourth, and let's keep it going, plus 1 over 120 times c1 x to the fifth, plus, oh my gosh, it was 0, so that's awesome. So every other even index after that, we don't need to include anymore. Let's keep it going. So c sub 7, that wound up being minus 1 over 3 times 7 factorial times c sub 1. Oh, I'll bet you'd like to see this page too. Times x to the 7th, and then we'll just throw on the old mathematical ... after this. Now, as far as two linearly independent solutions are concerned, your two linearly independent solutions go with the fact that you have two unknown constants. So what we're going to do is we're going to group them together. So all of the terms that contain a c sub 0, we're going to group them all together. The first term contained a c sub 0. That gave us a 1 if we factor it out. Then we'll have minus 8/3 x squared, and we also had one right here, plus 8/9 x to the fourth, and then there was nothing else that had a c sub 0 after that. Then we'll also group together everything that had a c sub 1 in it for our second linearly independent solution. So we had a